On average, Americans spend 90% of their time indoors. Buildings and cities have a huge impact on our comfort and well-being. Green buildings with lots of natural daylight, non-toxic materials, and superior levels of air quality and thermal comfort can have a big impact on well-being and productivity. Besides the impact upon those of us who live and work in the built environment, buildings also have a huge impact on sustainability through energy and material use. Buildings consume 50% of the energy and 75% of the electricity that flows through the US economy. Buildings use 40% of all raw materials globally. 15 trillion gallons of potable water are used in buildings annually, about 14% of the total. About 40% of greenhouse gases are sourced from buildings. The good news is that we can design buildings that produce more energy than they consume, harvest rainwater from the sky, and are filled with natural daylight, and are built of non-toxic materials. Buildings can be designed to be recycled when their useful life is over. And we can do this for about the cost of building conventional buildings of the same quality. As I've mentioned before, the American Institute of Architects has adopted a plan called Architecture 2030, whose goal is to transform the built environment from the major contributor of greenhouse gas emissions to a central part of the solution to the climate and energy crises. Architecture 2030 calls for all new buildings to be net energy producers by 2030, and for the renovation of older buildings to conform to these standards. Net energy producer means that the building produces as much or more energy than it consumes on an annual basis. Let's talk about some of the features of green buildings I've helped design. This building meets the Architecture 2030 standards today. It's the Schwartz-Geuich Sustainable Living Center. This is the home of the Sustainable Living Program at Maharishi University of Management in Fairfield, Iowa. I'm the co-director of the program, and my office is in this building. It's designed to be a living laboratory for the principles of building design that we teach. The building was built of local natural materials like earth blocks, whole tree timbers, and natural plasters and paints. We did some filming in a couple of classrooms in the Sustainable Living Center. Let me show you what an earth block looks like, and then how we make a building out of them and other natural ingredients. This is an earth block. It's made of material that we just dug from the ground. We rented a special machine, put the earth in the machine, and the machine can squeeze out enough of these blocks to build a house in a day. There's no other material in here, no concrete, no other filler, it's just earth compressed. All the walls that surround us in this building are made of this block. The students built 35,000 of these blocks for the construction of this building, and you can see them in the wall behind us right here. I'd like to talk a little bit more about how earth is used in this building. We saw in the big classroom how earth blocks create the walls of this building. And then we also cover those walls with an earth plaster. So this wall here is built of earth blocks, but then we've covered it with a natural earth plaster, which is earth we just dug up from the site here, mixed with a little bit of clay, sand, and chopped straw, and a little bit of manure from our local organic dairy. That's a traditional ingredient in a lot of earth plasters. Now, you notice this wall is dark. The clays we dig up here are dark, and the rest of the walls in this room are light. That's because we want to use daylighting in this building to light the building. There are ecological consequences for building solar panels and wind generators, and we want to use that energy wisely. The largest use of energy in this building is for lighting. So we can get all the light we need just by bringing light in from those high windows that you see here on this side of the room, and the high windows in the atrium that brings light into the center of the building. Light this classroom from both sides. We have low windows for views so that students feel like they're connected to the outside. In order to make the walls white, all we did was cover this natural earth plaster with a lime wash. So there's very little real paint in this building. It's mostly just earth, clay, sand, and a lime wash, so that we use mostly just natural materials. The Sustainable Living Center has a solar electric array, wind generator, solar hot water collectors, and a geothermal heat pump that produce 30% more energy than the building consumes annually. Let me show you around. First, the beautiful passive solar greenhouse. In ecological design, every major function in a system needs to be performed by many different elements. So in this building, we have 3 ways in which we heat the building and 2 ways in which we cool the building. The first way in which we heat the building is called passive solar design. In passive solar design, we have windows here that face south, We use all of the materials that you would use in a regular building, windows, concrete, steel, and we place them in such a way that we use our understanding of the flow of energy across the site and the different places that the sun finds itself in different parts of the year in order to heat the building almost for free, because it's all materials that we use in any building. So for example, these windows that face south, there's an overhang above them. And in the summertime, when the summer sun is very high in the sky, these windows are completely shaded so that there's no extra heat gain into the building in the summertime when we don't want it. But in the wintertime, in this latitude, the sun is only about 20 degrees off the horizon. It's just a little bit above the horizon, and the sun penetrates deeply into this room, hits against these walls, and heats the building. So that's the first way in which we heat the building. Now we're going to go talk about the second way, which is active solar design using collectors on the roof of this building. Now that we've learned a little bit about passive solar, the first way in which we heat the building, I want to tell you a little bit about the second way in which we collect and store solar energy for this building. It's called active solar. It uses one of two kinds of solar panels we have on the roof. Two kinds, one that make electricity and one that make hot water. The ones that make hot water collect the sun's energy in hot water and store it in this 5,000-gallon tank. Then we have pipes in the floor that when the building calls for heat, we can take this hot water and we can store several days worth of solar energy in this tank and distribute that throughout the building. These devices back here are called controllers, and what they do is they monitor the temperature of the solar collector and they monitor the temperature of the tank. When the temperature of the solar collector is hotter than the tank, it turns on a pump that will circulate the fluid and collect the solar energy and store it in the tank. Then when the building requires heat, if the passive solar gain isn't keeping up with the demand for heating for the building, then the thermostat in a room will turn on one of these pumps which circulates hot water from the tank through the floor into the building. So this pump, for example, is the big classroom that we were in first. This pump is the middle classroom, this pump is the greenhouse, and that's how the heat is transferred from the tank into the building. If we have an extended period of cloudy, cold weather in the wintertime and the passive solar and the active solar weren't keeping up with it, we have a third way in which we heat the building, and that's with a geothermal heat pump, which we'll take a look at next. Now, if the passive solar and the active solar aren't keeping up with the heat requirements of the building, we turn to our third way of heating the building, which is with a geothermal heat pump. Geothermal heat pump takes 1 unit of electricity and uses it to pull 2 or 3 units of heat from the ground. There's a network of pipes, thousands of feet of pipes that are about 15 feet in the ground, and the temperature at 15 feet is always about 55 degrees. It takes electricity to do that, but we use our solar and wind power to power the geothermal heat pump. In the summertime, we can also use it for cooling because it's much easier to reject heat from the building to the ground at 55 degrees than it is outside when it's 100 degrees out. And overall, the building generates about 35–40% more energy than it uses, not just for electricity, for computers and lights and PowerPoint projectors and things like that, but also for heating and cooling. So all the energy requirements for the building are matched, plus about 30% is given back to the grid. The building collects water for free from the sky through rainwater harvesting. It supplies water for all uses in the building, including drinking. The building processes all of its sewage waste. No utility bills, no water pipes in or out. And finally, let me take you just a short walk outside the building to the power shed and show you how all the sources of solar energy come together. The first thing that happens is all the wires that go out to the solar panels and up to the top of the wind generator come in on this pipe. Believe it or not, all the solar panels and wind generators have individual wires that come in here and come in down through this pipe. And then what happens next is very simple conceptually, but there's a lot of complicated technology that goes on in this box. On this side is the solar and wind generated electricity, and on this side is the utility, and this box makes the connection between the two. It turns the solar and wind generated electricity into better than grid quality power. And this converts the energy from the solar panels that are just outside this building on the ground. This converts the energy from the solar panels that make the overhang on the greenhouse. This converts the solar energy for the panels that are on top of the building. And this box converts the energy from the wind turbine into better than grid quality power. And right now, it's generating 6,000 watts out of 12,000. It's quite windy today, but it's not very sunny. And that's the beauty of the combination of wind and solar. When it's not sunny, it's often very windy. And you had a very steady supply of energy between the two. Now we're up to 2,900, 3,000, 4,000, 5,000, 6,000, 6,700. A while ago it was up to 12,000, so it went up to half of it. And it varies because the energy in wind is related to the wind velocity cubed. So every time we double the wind power, we get 8 times the energy, not just twice the energy. So for example, that means if we get a 10-mile-an-hour wind and we get a gust to 20, we get 8 times the energy. So right now, it's still around 1,000, but a minute ago it was up to 12,000, and that's the maximum. Today we're actually getting the maximum out of this wind turbine. Now I'm going to show you how everything comes together. The solar and wind generated energy, the building energy, and the grid. What happens in this pipe is the solar and wind generated electricity comes in here, the building energy gets taken off here, and the energy from the power company is here. So let's use as an example, let's say that we're generating 10 kilowatts of solar and wind energy and the building's using 2 kilowatts. So 10 kilowatts comes in here. Of that 10, 2 go off here and service the building. There's still 8 that need to go someplace. So they'll go out here and actually spin the meter backwards and put power out onto the grid. Now let's say it's nighttime and the solar is not generating any energy and we're just generating maybe 1 kilowatt from wind, but the building's requiring 3 kilowatts. So 1 kilowatt comes in here from the wind energy. It services one of the 3. We still need to get 2 from someplace. So those come here from the power company and they actually spin the meter forward and we actually buy some power from the power company. So this system does this all day long. There's no storage on the grid. In other words, none of this energy is being stored anywhere. What's happening when I push it out onto the power grid is that somewhere there's a fossil fuel generator that's backing off and using less fossil fuels. So we're saving fossil fuel by putting this energy out onto the grid from solar. The system we looked at a minute ago was a grid-tied system, meaning that takes solar energy, pumps it out to the grid, but the grid has to be functioning, the grid has to be turned on, the grid has to be active in order for that to work. If the grid is down, then you won't have any power. Even though you've got solar panels and sunlight, you won't have any power. I'm going to talk about a different kind of system called an off-grid system, which can operate independent of the grid, whether there's a power grid or not, whether you're 1,000 miles from the power grid. As long as there's sunlight, this system will operate. It has a couple of basic components. It has solar panels that take the sun's energy and turn them into electricity, no moving parts, nothing to wear out. We store that energy in batteries so that we have energy for if we need more energy at the moment than the sun's producing, or if we need energy at night, we have that energy stored in batteries. Another device is a charge controller, and what that does is it takes the solar energy from the solar panels and it moderates the flow so that the batteries don't get overcharged. It controls the flow of solar energy, so if we're not using energy, the batteries don't get overcharged and get damaged from that. Then we take the energy out of the batteries, the solar and wind generated energy out of the batteries, put it into a device called an inverter. What that does is it converts the solar and wind energy into better than grid quality power from the batteries, and it provides power to run all the appliances in your house, whatever you might need to run at the time. And so it's as simple as that. Solar panels through a charge controller to the batteries, charge the batteries up, then take energy from the batteries through the inverter to power your house. You might have noticed in the video the sound level changed in the shed, in the power shed, because it was a very windy day. And you could actually hear, when it got windy, you could hear the sound of the energy being converted from wind energy into grid power. And that was the changing value of the sound in the shed that you heard in the previous clip came from that. So here's another building. It's my home in Fairfield, Iowa. It's a climate responsive building. Every aspect of its design is tuned to the weather and climate of Fairfield, Iowa. It's off-grid and powered by solar and wind. I haven't paid an electric bill in more than 20 years. It harvests rainwater and treats its own sewage, so I haven't paid a water or sewer bill either. No pipes in, no pipes out. It's got high windows that flood the building with daylight. It's built of locally sourced materials like lumber and earth plasters. It's insulated with straw bales stacked up like bricks. I took everything I learned at my home and designed a housing project called Abundance Eco Village, which is powered by solar and wind, has a farm and edible landscaping, and uses rainwater for water supply. In Abundance Eco Village, the beers are cold and the showers are hot, but the homes, by design, use 1/3 to 1/10 the energy of a conventional home. We've found smarter ways to get better service from energy with ENERGY STAR appliances, extra thick insulation, sun-catching greenhouses on the south side, and earth tubes for cooling and ventilation. Once energy demand is reduced, it's cost-effective and practical to supply the smaller energy demand with solar panels and wind generators. There are 15 homes in Abundance Eco Village now, but when it's fully built out, there will be 30. One way to lower the ecological footprint of a house is to make it smaller. This house is an example of the not-so-big house concept. The owners moved from a 5,000 square foot house to this 800 square foot, well-designed house in the Eco Village, and they prefer it to their much larger old house. Do green buildings cost more? Well, it varies widely. Typically, there is a 10 to 20% premium for building a high-performance building. Green buildings use better quality, long-lived materials that sometimes cost more up front. But that increased cost is paid back in terms of increased comfort, energy savings, water savings, and maintenance cost, just as with solar panels for solar energy. There are two basic approaches to green building: natural building and high-performance conventional building. Natural building uses locally available, lightly processed materials. High-performance building uses conventionally available materials and building science to create buildings that require very little energy to heat and cool. The best buildings are 100% solar heated and cooled. By design, they use 75 to 90% less energy than conventional buildings. Note that some natural buildings are not high-performance buildings. They take considerable amounts of energy to heat and cool, and some high-performance buildings are not made with natural materials. Let's look at natural building in a little detail. Natural building uses lightly processed, locally sourced materials like straw bale, cob, rammed earth, adobe, wood, and stone. Earth plasters can be used for walls and floors. Some combination of clay, fibers like straw, and sand are common ingredients in natural building. Often, these structures are owner-built or involve a community building effort. My friend Susan in Fairfield and her husband John are building their own home and using lightly processed, locally sourced materials like straw bales, local timber from their land, and earth plasters. The Great Courses crew and I visited her home to see how she mixes and applies her own homemade plaster to the outside of the home.
Hi, my name is Susan. Welcome to the farmhouse at Hickory Highlands. I'm going to do a demonstration for you of an exterior plaster on a straw bale wall. The base coat has already been applied and is dry. So we're going to wet the wall, and then we're going to do our skim coat of our last coat of 1 clay, 2 sand, and a half a part of a manure straw mix. The manure helps to add a little bit of fiber and water resiliency. So we start with water. I'm going to do about a half of a part. So I'm putting in 1 gallon of sifted clay. This is my own just subsoil here in Iowa. Our subsoil is pretty much pure clay. I put it through a hammer mill to get it all broken up like this. So that's 1 clay. Then we'll do 2 of sand. I'm just going to do a little bit so I can get it mixed up a little bit. This is going to make some noise. So right now we have a half water, 1 clay, and 1 sand. Plaster recipes are quite variable. Depends on your subsoil and how much sand is naturally in your subsoil. You might be adding more sand or less sand to get a good plaster mix. then we have some lovely cow manure from our sacred cows. And I'm just going to put in a little bit. The water varies, depends on how wet your sand was, how wet your clay was. I'm going to put in some chopped straw. This was also chopped in the hammer mill, nice and little pieces. About a half a bucket when I combine it with the manure. All right, now I'm going to apply it. I have a hawk. I have 3 different trowels. I have a metal trowel, a wood trowel, and a plastic trowel. Wet it. Sticky. So it's going to stick to the wall. You want to dampen your wall first so that your coat that you're putting on will stick. You want to start wetting your wall ahead of time so the water has time to soak in. Many different ways you can do it. You can take it from the front and go up this way. You can take it from the back and go this way. If you're not comfortable going like this, if you're new at it, you tend to drop more on the ground than you get on the wall. So what some people like to do is they just put their hawk right up against the wall and push. Doesn't matter. You just get it on the wall. So if this was a final coat, you would use a steel trowel to make it quite tight, especially if you're inside.
This is not a new or particularly unusual way to coat the walls of a house. About 50% of the people on the planet live in earth houses, and there are lots of examples from around the world. The town of Roussillon in southern France has long been known for the production of beautiful pigments from clay and earth deposits near the village. Both insulation and thermal mass are useful in sustainable building design, but they have very different functions and you can't substitute one for the other. Insulation blocks the flow of heat in or out of a building, and it is typically made from light, fluffy materials. It's like wrapping a building in a nice down comforter. Thermal mass stores energy as it rises in temperature and releases it as its temperature drops. It's used for keeping a space from overheating during the day, storing excess solar heat for release into the space at night. Thermal mass materials are dense and heavy like rock and concrete. In the Sustainable Living Center, the earth block interior walls have 10 inches of insulation on the outside. The earth blocks help keep the interior temperature constant, and the insulation slows the flow of heat in and out of the building. Now, on the other hand, high-performance building uses conventional materials that, for the most part, will be familiar to building contractors and available at your local building supply store. Most building contractors can adapt to the novel ways these materials are used in high-performance building, but it's best to find a builder that is educated about it and committed to it. High-performance building combines intimate knowledge of the climate, the site, the materials, and building science to create buildings that require very little energy to heat and cool. Here's what you should consider in creating a high-performance building. Start with green features that you can get for free. Passive solar design uses common building materials to collect and store energy, provide abundant natural light and ventilation. Remember, it's passive, solar because there aren't any pumps or fans used to move the energy. Common building materials like windows, wood, and massive materials like concrete can be placed in such a way that the building, by design, collects and stores solar energy in the winter and rejects solar energy in the summer. It makes optimum use of the energy that flows over your site in all seasons. It's mostly free because it's just a more intelligent approach to placing building materials that, for the most part, you would have used anyway. You trade more intelligence in design for less building energy use. It's important to consider passive solar in the early stages of design because obviously it's difficult to change the orientation, shape, window placement, and insulation levels of a building after it's built. Here are a few tips for passive solar. First, build a rectangular shape and orient the long side east-west. This maximizes solar exposure for winter and minimizes for summer. Favor window placement on the south to maximize solar gain. Windows need an overhang size to block high summer sun and allow low winter sun to penetrate deeply into the building. 10 to 15% of building floor area in south-facing windows is about right. You can overdo this and cause the building to overheat during the day and use too much energy at night, so pay attention to your measurements. Locate heavy materials like concrete and tile where the sun will shine directly on them to help store solar energy for use at night. The sun spends a lot of time shining on the west side of a building during the summer. Minimize windows on the west to avoid heat gain in the summer. Daylighting is the art and science of lighting buildings using sunlight. As you saw in the classroom video, for daylighting, windows need to be placed to allow indirect sunlight into the room. Direct sunlight is too intense. Daylight windows are often placed higher, with view windows at a lower level. You will have to spend a little extra money for insulation. For the colder parts of the US, you want about 12 inches of wall insulation and 20 inches of insulation in the ceiling or attic. Remember that the extra money you spend on insulation can often be recouped through savings in downsizing or eliminating the furnace. Seal the building tightly and provide fresh air using an air-to-air heat exchanger. Air-to-air heat exchangers allow the heat in exiting warm air to be passed by incoming cold air, allowing abundant fresh air with a minimum energy penalty. These guidelines apply mostly to new construction. I'd like to make a distinction between energy conservation and energy efficiency. Energy conservation is doing less with less, having a colder house to save energy, freezing in the dark. You might also want to consider modest lifestyle changes, these energy conservation measures, like wearing a sweater and adjusting the thermostat higher or lower. It couldn't hurt. But energy efficiency is doing more with less, having a more comfortable house that uses less energy, hot showers and cold beer, just being smarter about how we heat the water and cool the beer. In keeping with the theme of sustainable living as a radical redesign for a better way of life, we're going to consider some of those energy efficiency measures next. Start with a professional high-level energy audit. This is different than most free walkthrough audits offered by utility companies. Expect the audit to take most of the day and cost $300 to $500. You'll get a prioritized list of options for improving energy efficiency and comfort, as well as an estimate of energy savings for each option. What can you do with what you got? How can you retrofit a home or apartment for sustainable living? I have to be honest with you. Retrofitting an existing home to a high-performance standard can be difficult and expensive. We talked about some ideas in our lecture on energy, and here are a few more. Cutting down air leakage. Do weather stripping. Often utility companies have incentives to help pay for this. Caulk around windows. Put on seasonal storm windows and weather strip around the doors. Seal the holes in your house. Seal around pipes, wires, electrical outlets, and other penetrations. The next thing to do is add insulation. Attics are easy places to add more insulation. Aim for R60 in the attic and R40 in the walls. R value is a measure of the ability of a material to block the flow of heat. Higher numbers are better. Cellulose, made from old newspapers, is a common attic retrofit insulation. Attic insulation is a good do-it-yourself project, and most places that sell cellulose insulation will loan you the machine that blows it into the attic. Be sure to seal up any leaks from the house into the attic before adding insulation. If your house is old and doesn't have any insulation in the walls, you can blow cellulose or foam into the walls. Unlike attic insulation though, wall insulation is best done by an experienced installer. Replacing windows can be pricey, so consider insulation first. The next thing to consider is improving the efficiency of your heating and cooling system. Seal the heating and cooling ducts. Test to see if your furnace is operating at peak efficiency with a combustion efficiency test. It's also important to check that sealing air leaks doesn't trap combustion gases in your home. Retrofitting an existing home is not easy. The most efficient way of doing so is an area of continuing research. Now, speaking of furnaces, let's look at a couple of other heating systems. Wood is stored solar energy and makes a good backup heating source for passive solar homes. Modern wood burners are efficient and clean burning. I use a wood burning stove as the only source of heat in my well-insulated straw bale home. If you use solar electricity, consider mini-split heat pumps. Mini-splits take 1 unit of electricity and produce up to 3 units of heat and provide efficient cooling as well. I'm designing a new home for my family, and it will be heated and cooled by a mini-split powered by solar electricity. Ground source heat pumps are expensive at the small capacities needed for low-energy homes, but can work well for larger buildings. Ground source heat pumps use the stable temperature of the earth at depths of 8 feet or more to provide heating and cooling. Buildings and cities have a huge impact on human well-being and sustainability. The biggest part of our ecological footprint comes from the built environment. Using the principles outlined in this lecture, you can begin to see how we can build buildings that are regenerative, that give back more than they take, that are sustainable.